Okay, so in this video, I'm going to talk about various types of oxidation and reduction. So I'm not going to go through all of them, but go through some of them, especially ones involving epoxides. So oxidation, broken down simply, is the increase, especially in organic chemistry, is the increase of oxygen content in a compound, whether it's going from one oxygen to from 0 oxygens to 1 oxygen to 2 bonds to oxygen, 2 bonds to 3 bonds, by making a carboxylic acid, or going all the way to CO2. Reduction is going to be removal of these bonds and the increasing of hydrogen content. So the simplest thing we can do is catalytic hydrogenation, which is simply we're breaking down double or triple bonds in the presence of hydrogen, especially excess hydrogen, but hydrogen, in various different metal catalysts. This is asymmetric addition, but can generate chirals. So it's going to be adding syn across the metal. So platinum, palladium, nickel, rhodium, ruthenium, all these are going to add. But essentially, it's going to generate an alkane from alkene or alkyne. Essentially, it's we have a metal surface. We have some groups that can add here. We have the alkene or alkyne adding to 2 metals, and the hydride adding to 2 positions nearby. And once they're sitting on there, essentially it's easy enough to transfer them across. And it's going to keep transferring until there's no more rings, essentially, until there's no more double bonds, and so it has to leave. Now, as we'll see later on, maybe not in this video, but later on, there's ways to essentially stop this from alkyne to alkene and not go all the way down. But once you go to alkene, it's actually so much easier. It takes some effort to stop it part way. Okay, so epoxidation is one thing we'll do. There's multiple different ways to add peroxide. You could just add peroxide itself, but there's one particular peroxide that's commonly added. You got to learn the name. MCPBA. It's a peroxide. It's metachloroproxybenzoic acid, if I remember right. So breaking down what that means. Metachloro, so there's a chlorine meta to the benzoic acid. Benzoic acid, peroxybenzoic acid, that's basically this metachloroproxybenzoic acid. It is a very convenient, very stable peroxide that we can keep around and use, and it doesn't cause a whole lot of problems. So we need to be familiar with this. So if you see a MCPBA, you know that's a peroxide. That is a peroxide that's going to react. A peroxide plus an alkene is going to form an oxirane. An oxirane. So a 3-membered ring. And this 3-membered ring can then open up in the presence of a nucleophile. So what's going to happen? How does this work? So you have a ring and you have a peroxide. So the peroxide looks something like this. So the the ring attacks this oxygen. This bond goes to the carbocation that's formed. The lone pair attacks this hydrogen. This thing shifts up to place the lone pair, and this carbon goes down to reform the carboxylic acid. So as we form there, we have made our ring, and we have turned what was a peroxybenzoic acid into a standard acid, standard carboxylic acid, or standard benzoic acid. So essentially the carbonyl and the hydroxy group switch places. But so we've essentially made an oxy ring via syn addition. It is sitting down on this double bond, locking it in place. So if there was a hydrogen and whatever R group and R group, so we have trans, that's going to lock this into this chiral conformation. But like most three-membered rings, like most three-membered rings, this oxirane is not particularly stable. There's a lot of steric hindrance here. Not steric hindrance. There's a lot of ring strain here, and that just a moderate nucleophile and electrophile, we can ring open this. So acid catalyzed epoxide ring open. Strong acid epoxides will favor it. So let's look at this. Okay, so let's clear this real quick. So draw that. We have our ring. So let's keep our steric hindrance here. So first, acid is the ring attacks the acid, forms our carbocation. Come on, go away. Okay. Forms not a carbocation, sorry. Forms this destabilized oxygen cation, which then allows water to attack. And it's always going to be anti to the one oxygen, so I could either attack here or there. I'm going to attack on the right, and so cause that to swing up, and and of course we have to regenerate our acid. We have to regenerate our acid, so that's going to remove that hydrogen down there. This is always going to be anti-addition. Whenever we're attacking where it's a two-step and this forming this ring, it's always going to be anti. Whenever it's going to kind of when we form this ring, it's always usually going to be anti-addition. When it sits down across the double bond with the two bonds at once, it's going to be our syn typically. So a two-step addition is usually anti, or one-step addition usually syn. We can do osmium tetroxide. So That's a weird one. That's a syn addition. But osmium tetroxide dihydroxylation. You could do this, but it's toxic, but it's pretty good yield. So the basic thing is, let's say, go ahead and add. So you add osmium tetroxide, and then we add some sort of peroxide or nitroso compound. Peroxide or some sort of and sorry, screw that up. Let's see. So the first thing is we add osmium to this double bond. That forms a five-membered ring with the osmium. And then from there, the peroxide removes those rings and reforms your osmium catalyst. So note, osmium oxide again. So note, how did this add across the double bond? It added in a five-membered ring, so it added to both sides, and essentially when we did the peroxide, it cleaved there and turned those into alcohols. It didn't cleave this bond or that bond, it cleaved this bond here, which is why it's a syn addition. Let's see, oxidative cleavage by permanganate. Depending. Now, this is an interesting one. Permanganate is a really strong oxidizer. Depending on what you want to do with how you use it, you could get multiple products, but it works under a similar idea. If I have an alkene, if I use cold dilute, permanganate, and then the first step and the second step we use OH minus and water, you get our syn addition of dehydroxylation. What's happening? You form your Mn. The same thing. Oh, not a double bond there. It's a single. Shoot. O minus. And then the hydroxide and the water help neutralize this and cleave that bond. So you have your syn addition of your alcohol and MnO2. Now, however, if you instead do this concentrated and hot, you get over-oxidation. If I do that, so MnO4, you still form the same byproduct. You do that the first time, you get your syn addition of the alcohol, but because it's concentrated and it has enough energy to keep going, it's going from there cleave that bond and continue oxidizing. So and depending on what you have, you can keep oxidizing. So go all the way to carboxylic acid or even CO2. So a better example would be this. Okay, if I had this guy. So this is our 1, 2, 3, 4 B. 2-methyl 2-butene. 2-methyl-2-butene. If I used the hot concentrated permanganate, it's powerful shit. You would first have, as I said, byproduct wise, alcohol, but then it's going to keep cleaving. It's going to cleave that and then oxidize that alcohol to a carbonyl group. So you would form a ketone and an aldehyde, but the aldehyde would keep going. And so you would end up with a ketone and a carboxylic acid. In that case, you would get acetone and formic acid. No, sorry, acetic acid. So, you got to be careful. Hot, when we're warm and concentrated, going to kick everything's ass. So if you want to stop it at the first oxidation, use cold and dilute. Make sure you don't have too much and it doesn't have too much energy. Another one that works similar is ozone analysis. It's partial oxidative cleavage. It does part of the steps of the permanganate, but doesn't go all the way. So take the same starting point. We add ozone, and then what actually happens is we form this intermediate, as you'll see, which is not particularly stable. It's easily oxidizable off. The intermediate is going to be cleaved off. So this intermediate actually rearranges itself. It rearranges itself by going boop. It's kind of cool. That drops there. And we have a lone pair from this guy swinging into this. So what you have, you end up forming this guy real quick. And this guy, which isn't really stable, which this guy attacks there. Sorry, that attacks there. That goes, that double bond swings here, and that swings over there. That swings over there. And basically it rearranged itself into, when you do the ozone, it rearranged itself into this compound. And this compound is what hangs around until we are ready for the next step. So instead of a 3-oxygen 3-oxygen bond, we still have a 5-membered ring, but now that 5-membered ring is only a peroxide and not an ozone ring. So this is ozonide, and this ozonide is easily reducible. So the next step is we use a dimethyl sulfide. This dimethyl sulfide is easily oxidizable. So in the presence of this easily reducible compound, this guy has a bunch of oxygen, wants to give it up, and sulfide is more than willing to take it. So that sulfide is what's going to push this to the next step. So, and of course, you're going to have DMSO, dimethyl sulfoxide. So, step 1, we use ozone at -78 degrees because ozone is not very stable. We don't want to decompose it unnaturally. Step 2 is we just use our dimethyl sulfide, which is what? CH3 2S. So, but this is all types of oxidation and reduction. So, this is, yeah. So, just wanted to introduce these. This is the basic concept of most of our oxidation and reduction. That essentially we are breaking these down. We keep a stable compound. Depending on the conditions, it could form one thing or the other. Some of these guys are going to strong oxidizers. You want to try to learn the strong oxidizers, and those are going to keep oxidizing to a certain point. And you have certain weaker oxidizers that are only going to add 2 diols or whatever. So looking at those will help. Okay. That's where I'm going to stop. Thank you for your time.